Hello everyone, today we are going to learn the concept of reaction intermediates. In chemistry, reaction intermediates are generated in a chemical reaction which will be a short-lived, high energy and highly reactive molecule that is quickly converted into a more stable molecule. For example, in a reaction, AC reacts with B and gives AB and C. It looks simple, but actually what happens is AB reacts with C and forms an intermediate ABC that is then converted into the product. It is a non-concerted reaction, that is, it involves more than one step. Before going to the details about it, we should first learn the types of cleavages. Okay, we know that the chemical reaction happens by bond breaking and making. That is, breaking of existing bond and making of new bonds. The bond breaking, that is cleavage, can happen in two ways. One is heterolytic cleavage and other one is homolytic cleavage. Heterolytic cleavage is the one where during the cleavage of bond, the shared pair of electrons is taken away completely by one of the atoms, relatively with the more electronegative one. This results in the formation of charged spaces, that is positively and negatively charged ions. Homolytic cleavage is the one in which during the cleavage the shared pair of electron is distributed equally between the two atoms. That is, each atom departs with one electron each. This results in the formation of free radicals. Now let's discuss the types of intermediates in detail, such as carbocation, carbanion, free radicals, carbenes and nitrines. Carbocations results by the heterolytic cleavage. Here, carbon donates its shared pair of electrons to the leaving group. Here, carbon carries the positive charge. For example, in the case of haloalkanes, the removal of halide ion results in the formation of carbocations. Similarly, alkene and alcohol in acidic medium produces the carbocation. In carbocation, the carbon is bonded to three different atoms or groups and it is trivalent species. It has only 6 electrons surrounding it. Hence, it behaves as an electron deficient species in order to attain 8 electron configuration. It is sp2 hybridized carbon with the vacant p orbital, and overall the geometry of carbocation is planar. Okay, coming to the stability of carbocation, if we compare the stability of alkyl carbocation, the tertiary carbocation is most stable. Then comes secondary, then primary, and then methyl carbocation, which is least stable carbocation. The order can be explained on the basis of two factors. One is inductive effect and other one is hyperconjugation effect. Carbocation is positively charged and electron deficient species, as we discussed earlier. The nature of alkyl group is electron releasing. In the case of tertiary butyl carbocation, there are 3 alkyl groups attached to the carbocation. These alkyl groups will decrease the positive charge on carbon, thereby decreasing its electron deficiency. There are 3 alkyl groups in tertiary butyl group. So, the positive charge is delocalized. These alkyl groups will decrease the positive charge on carbon, thereby decreasing its electron deficiency. That is, more the number of alkyl group, the more will be this plus I effect. Therefore, more will be the delocalization of positive charge and more will be the stability of carbocation. The stability of alkyl carbocation can also be explained by hyperconjugation effect, where sigma bond is involved in conjugation. I hope you all remember that it's also called as no bond resonance effect. In case of carbocations, the sigma bond between carbon and hydrogen involves in delocalization as shown here. Hence now the positive charge is delocalized to this hydrogen atom. Here I have shown 3 resonating structure by the involvement of 3 hydrogen atoms. Similarly, the other methyl group will also involve in resonance. Hence, it results into 9 resonating structure. And if you consider secondary carbocation, where we have 2 alkyl groups, hence there is possibility of 6 resonating structure, whereas primary carbocation can give, that is ethyl carbocation can give 3 resonating structure. We know that more the number of resonating structure, more will be the stability. Hence, tertiary carbocation is most stable. The other cations such as allyl and benzyl carbocations can be explained, their stability can be explained through resonance effect. If you see allyl and benzyl carbocation, they are looking like a primary carbocation. However, it is much more stable compared to primary carbocation. So the given allyl carbocation is primary and it is highly stable due to resonance effect. So the resonance hybrid can be given like this. So this stabilizes the system. Similarly, in the case of benzyl carbocation, that can be stabilized by resonance effect. In these cases, the vacant p orbital on carbon bearing positive charge is in conjugation with pi bond, and thus delocalization occurs through p-pi overlap. In the case of carbocation containing phenyl groups, the triphenyl methyl carbocation is most stable compared to secondary and then primary, because more the number of resonating structure is possible when we have more number of phenyl, where carbon retained its shared pair of electron results in the formation of carbanion. In this case, carbon carries negative charge. It can be generated by the attack of nucleophile on a neutral molecule. It can also be generated by the removal of hydrogen atom from a carbon in the presence of a strong base. Here, carbanion is attached to 3 different groups or atoms. Here also it is trivalent. It has 8 electrons in it. That means it attained octet configuration. So it behaves as an electron-rich species. Here in carbanion, carbon is sp3 hybridized, where one of the hybrid orbital has a lone pair of electron. Hence, it has an overall pyramidal geometry. Coming to the stability of carbanion, the stability of alkyl carbanion can be explained by the inductive effect. The order follows as shown here. Methyl carbanion is most stable, then comes primary, secondary and tertiary carbanion is the least stable one. As we discussed earlier, the alkyl group is electron releasing in nature. This increases the negative charge on carbon atom and destabilizes the system. In tertiary butyl carbanion, there are 3 alkyl groups. Releases the negative charge on the carbanion. This accumulates more negative charge on carbon atom. This destabilizes the system. Hence, tertiary butyl carbanion is least stable. Next, secondary, which has 2 alkyl group, to some extent that destabilizes the system. So whereas the methyl one, where there is no alkyl group, so methyl carbanion is most stable. So this is the reason the excess buildup of negative charge on carbanion destabilizes the system in the case of tertiary carbanion. Stability of allyl and benzyl anion can also be explained by resonance effect. Here also, comparing with primary carbanion, the allyl and benzyl carbanions are most stable due to resonance effect. These carbanions represent conjugated system where the lone pair on carbon participates in delocalization with pi bond. P-pi overlap. This results all the carbanions in allyl and benzyl anion into sp2 hybridized. This leads to the planar geometry of the system in the case of allyl and benzyl carbanion. If we compare allyl and benzyl carbanion is more stable because more number of contributing structure. Similarly, the di and triphenyl methyl carbanion are more stable compared to benzyl anion. In diphenyl methyl carbanion, the negative charge is delocalized over 2 benzene rings, whereas in triphenyl methyl carbanion, the negative charge is delocalized over 3 benzene rings. Thus, the order is as given here. The triphenyl methyl anion is most stable, whereas benzyl carbanion is least stable. Next type of reaction intermediate that we are going to discuss here is free radicals. Free radicals are generated when homolytic cleavage of bond takes place, as shown here. In general, free radicals are formed in the reaction which occur in the presence of light or at high temperature or in the presence of organic peroxides such as benzoyl peroxides. Free radicals are the species with a single electron and thus they are electron deficient in nature. A carbon free radical is sp2 hybridized with a p orbital carrying single unpaired electron in it. Hence, a free radical has a planar geometry. The carbon in free radical is trivalent and has 7 electrons in it. We can also explain the stability of alkyl free radical by inductive effect and hyperconjugation effect. It is similar to the carbocation. Since it is electron deficient in nature, more the number of alkyl group, more will be the stability. Hence the order follows as shown here. Tertiary radical is most stable, then comes secondary, then comes primary, and methyl free radical is least stable. Similar to carbocation, here also we can explain the stability on the basis of hyperconjugation effect. So the next one is carbenes and also nitrines. They are all neutral species. Carbenes are neutral species, have divalent carbon with an unpaired electron pair in it. Nitrines are analogous to carbene. It is monovalent and has 2 unpaired unshared pair of electron on carbon atom and nitrogen atom. Nitrines are considered as the nitrogen analogous of carbene. It is monovalent and has 2 unshared pair of electron on nitrogen atom. Both are electron deficient and highly reactive species. We will discuss in detail in some other video about carbenes and nitrines. Thank you all for kind attention and happy learning. See you.